Alternative solution concepts. In light of the conclusions of the previous section, a natural way to advance would be to re-examine the solution concept that we are using. In section 12.3, we saw that randomization certainly helps, but also carries with it some disadvantages. However, in some cases, randomization is not known to help, and additionally, sometimes we want to stick to deterministic mechanisms. What other solution concepts that fit the worst-case way of thinking in CS can we use? One simple thought is that algorithm designers do not care so much about actually reaching an equilibrium point. Our major concern is to guarantee the optimality of the solution, taking into account the strategic behavior of the players. One way of doing this is to reach a good equilibrium point, but there is no reason why we should not allow the mechanism designer to leave in several acceptable strategic choices for the players and to require the approximation to be achieved in each of these choices. As a first attempt, one is tempted to simply let the players try and improve the basic result by allowing them to lie. However, this can cause unexpected dynamics as each player chooses her lies under some assumptions about the lies of the others, etc. We wish to avoid such an unpredictable situation, and we insist on using rigorous game-theoretic reasoning to explain exactly why the outcome will be satisfactory. The following definition captures the initial intuition without falling to such pitfalls. Definition 12.35 Algorithmic implementation. A mechanism M is an algorithmic implementation of a C approximation in undominated strategies if there exists a set of strategies D such that one M obtains a C approximation for any combination of strategies from D in polynomial time, and 2 for any strategy not in D. There exists a strategy in D that weakly dominates it, and this transition is polynomial time computable. The important ingredients of a dominant strategy's implementation are here. The only assumption is that a player is willing to replace any chosen strategy with a strategy that dominates it. Indeed, these guarantees at least the same utility, even in the worst case, and by definition it can be done in polynomial time. In addition, again, as in a dominant strategy implementability, this notion does not require any form of coordination among the players, unlike Nash equilibrium, or that players have any assumptions on the rationality of the others, as in an iterative deletion of dominated strategies. However, two different from dominant strategies implementation are worth mentioning. One, a player might regret his chosen strategy, realizing in retrospect that another strategy from D would have performed better, and 2, deciding how to play is not straightforward. While a player will not end up playing a strategy that does not belong to D, it is not clear how he will choose one of the strategies of D. This may depend, for example, on the player's own beliefs about the other players or on the computational power of the player. Another remark about the connection to the notion of implementation in dominated strategies is in place. The definition of D does not imply that all undominated strategies belong to D, but rather that for every undominated strategy, there is an equivalent strategy inside D, i.e., a strategy that yields the same utility no matter what the others play. The same problem occurs with dominant strategy implementations, e.g. BCG, where it is not required that truthfulness should be the only dominant strategy, just a dominant strategy. In this section, we illustrate how to use such a solution concept to design CAs for a special class of single-value players. The resulting auction has another interesting feature. While most mechanisms we have seen so far are direct revelation, in practice indirect mechanisms, and especially ascending auctions, players compete by raising prices and winners pay their last bid, are much preferred. The following result is an attempt to handle this issue as well. Single-value players, the mechanisms of this section fit the special case of players that desire several different bundles, all for the same value. Player I is single-valued if there exists Vi bar, which is greater than or equals to 1, such that for any bundle S, Vi of S is in the set either 0 or Vi bar. That is, I desires any one bundle outside of a collection Si bar of bundles for a value Vi bar. We denote such a player by Vi bar, Si bar. Vi bar and Si bar are private information of the player. Since Si bar may be of a size exponential in M, we assume the query access model as detailed below. An iterative wrapper. We start with a wrapper to given an algorithmic procedure which will eventually convert algorithms to a mechanism with a small approximation loss. It operates in iterations with iteration index j and maintains the tentative winners wj, the sure losers lj, and a tentative winning bundle Si to the j for every I. In each iteration, the sub-procedure is invoked to update the set of winners to wj plus 1 and the winning bundles to S to the j plus 1. Every active non-winner then chooses to double his bid, Vi to the j, or to permanently retire. This is iterated until all non-winners retire.